Okay, why don't we start talking about Unit 7? So on Tuesday, I had to go down and take students on Monday and Tuesday down to the Twin Cities to do a presentation they were doing for an Innovation Scholars activity. So I wasn't able to be in class. So I'm going to maybe talk a little bit more today than I do on a normal Thursday. Um, but I just wanted to, hopefully you've gone through the learning resources and stuff, but I just want to highlight a couple things in the learning resources in case you missed them here. So in this unit, we're going to really look at analyzing sequential data. And we often call this time series data, data that occurs at a set time there. And so like the classical version of this is like predicting stock prices here. So like when we talk about this data, we might think of data like this that goes up and down over time, or sales like this, or data like this. In this picture, the black line is kind of the actual data, and at some point, we start predicting the data going forward here with the blue lines. So again, we're predicting that. Then again, a lot of it is just like financial data, stock data, sales data, things like that. Now, there are a lot of other things that fall into this category that you may not guess right away, like sound and music. Again, that's sequential data. We have this pattern of time. So besides generating stock forecasts, it's not that different to generate some music or some sort of sound there. And language and words fall a lot into this sequential pattern because letters or words go in a certain order and they're dependent on the previous words in the sentence there. So a lot of today's large language models are outgrowth of this sort of sequential, predicting sequential data for this. So that's what we're going to kind of look at. We're going to look at recurrent neural networks. The traditional neural network has layers that feed forward to the next layer that feed forward to the next layer. And then when we get a new input, we clear out the whole network and try to do it again. If we have a new picture, we put the new picture in here, we calculate all the convolutional layers, whatever, calculate the output, get an output. And then if we have a new picture, we kind of clear out the network and put the new picture in here. So, and then see what that is there. But the network never, remembers what the picture was before or the input was before. It only sees the current input. But with time series data and recurrent networks, we want to have a little bit of memory here. So there'll be some sort of like feedback from maybe an output layer will feed back to the input layer. So one way to think about it is that we provide an input, we have a hidden layer, we process that, we process this. And then when we're going to do the new input, we put in the new input there, but we also copy the output back into and feed it as input to the hidden layer too. So there's some delay. So another way of thinking of that is there's a recurrent connection and it's a time delay. So the hidden layer might see the current input and the previous output, or the current input and the previous hidden layer sort of stuff. So often it is seeing some stuff from the previous input. And that's important with these long short-term memory stuff. Now, besides normal recurrent networks, there's two more complicated versions, and we're not going to get too much into these. One's called long short-term memory, and the other one is called gated recurrent units, GRUs here. And they all have more complicated structures here. They take the current input, but they also take the input from their own nodes, the hidden layer, kind of from the previous update. And that's what this kind of shows. The bottom is the new input, and anything from the side is the inputs from the last update, the last time cycle. And again, anything that's going out on here is, again, going to maybe the next output. So we used to talk a lot about these, and I have lots of cool articles and lots of cool descriptions here of these, and they're still used some, but a lot of this stuff is kind of fallen out of favor. So we're not going to deal as much with these as we used to, because some of this stuff has been replaced by newer methods. Okay, so we're processing this data. Again, one thing we use is use it to generate text. We used to do this in Unit 9 and 10, and then Unit 7 here. And again, you can walk through a notebook for generating text here. And again, this was like cutting edge 5 years ago, and it's just amazing how out of date it seems now here. So what we were doing then was we were taking books like Alice in Wonderland or The Wizard of Oz or the Bible, feeding them in character by character and training a network to predict the next character. So one thing that's nice about sequential data is that you have some you don't necessarily have to like categorize stuff or figure out what you're going to predict, like with pictures of dogs and cats. You have to have, say, some student to look at lots of pictures of dogs and cats and say, this is the dog and this is the cat, this is the dog. With sequential data, that's kind of built in, because what we do a lot is we give our network like a set of text and then predict the next character in the text for this. So again, here we're trying to feed in, this looks like Alice in Wonderland for this. We take our text and break it down into characters here. We feed it through our network. We set up our recursive network, which is just some of these either GRU or LSTM layers for this. Then we train the network on a bunch of this data. So we'll feed it a sequence of letters and see if it'll predict the next one. So like here, we're feeding it how, R, and then Y, O. And you'd think the next letter, and when I think of it, I think probably Y, O, U, for U would be the next letter. And then we see what it's going to predict. And we have it try to predict the next letter. And it's predicting T, and then all, she, wand, and the wall. So it's predicting words pretty well, but it doesn't put the words together at all into sentences for this. And again, we can try different ways of doing this, encoding different things. And again, 5 years ago, we were looking at it. Do you encode characters? Do you encode words? While you encode, what do you feed to a model like this? So. One thing we did find with these recurrent neural networks is something called attention was developed. And we'll be talking about attention because we see that attention is all you need going forward. What we'll do is we'll leave the attention. Once you add attention to these networks, we'll then look at them, and Google will say, it has a very important paper that looks at that and says, well, what if we just keep the attention stuff and get rid of the recurrent stuff? One of the problems with the recurrent networks is that they don't train really fast. One of the great things about a lot of this stuff is we can do a lot of it in parallel here. But with recurrent, just the way that, since you have to feed one thing to it and then you have to make a copy of that and copy it back and input and feed the next thing, it's very sequential training, and you can't parallelize it very well, and you can't make it very fast. And so there's this thing. Let me try to explain what attention is real briefly. So here's a good visualization of these networks here. I'm gonna scroll down to the bottom of this article. So again, what we're feeding in here is a set of characters or words, and they're encoded into some internal meaning. And then that is sent to a bunch of decoders, which convert that into a meaning again and generate like the next letter or the next word in our sentence here. So we have these encoders and decoders. What we found is that we want to look at some relationship between the words, the words going in and the words coming out. And like if you're looking at a sentence and you're trying to predict the next word, there are some words in the previous 5, 10 words, previous sentence, which are important to know about, and some which aren't there. And we want to try to figure out which words in the previous words, in the previous sentence or, that we've looked at so far are important, which ones aren't here. So they looked at different ways of doing different functions in here to do that. And eventually they come up with this, what is called an attention mechanism. So we feed in different words that goes to the decoders, but it also goes to an attention mechanism. And that tells us how important these words are in decoding or figure out what the next syllable or sentence should be for this. So, for example, if you want to translate one sentence to another, let's say we're translating, this looks like it's English to French. And we have the sentence, the agreement on the European Economic Area was signed in August 1992, and we're going to generate the output in a different language here. Certainly, so, the word "the" is important to this translation there. But there are some areas like European Economic Area where it's important to have all 3 words together kind of impacting your output here. So we see that it's not just the word that helps predict what the corresponding French word is. There are some areas where where we need to attend to different things in the sentence for this. So this is trying to show with the bright colors which words here are important to attend to when generating these words here. I linked in there was another link here to another article, but that was gone. This is an IBM article on attention, and it goes over a good detail here. But so in attention that we use today, there are things called query keys and values, and there's all this little matrix math for calculating query keys and values here. Query keys and values here. And we often have these abbreviations for these V, K, and Q for this attention stuff. Some people like to do a deep dive and learn how that works. And especially if you are familiar with like matrix multiplication and some of that sort of stuff, it's interesting to see how it works. But again, generally you don't need to know how that works. You just know that there's an attention mechanism. There's some cool math that goes into calculating. If I see a series of words, I can then train this matrix multiplication or train these kind of vectors so that it'll predict how important each of those passwords are in predicting the next word for this. It's I see it kind of like convolutional neural networks where we create these filters to look at images. There's not a clear way of interpreting that, but again, we're training these filters, but the filters are predicting how which previous words are important in predicting the next word. We'll just mention one more thing is that tokenization. Originally, we were trying to figure out how to tokenize like characters and stuff. Um, and we originally were trying to just characterize letters in some ways. And so you could say maybe it's a number between 1 and 26, but that's not very useful because if you can characterize them as numbers, then two letters that are next to each other in the alphabet kind of imply that they might have the same meaning there. So like T and U, like letters 19 and 20 there, that I mean, they're no more related than any other letters, but if you just give each one a number, they're very close numeric. So why are they very close numeric if they're not, similar to each other in some ways? So just assigning letters to numbers doesn't work very well. We then use this one-hot encoding possibly to do letters. And then so you need 26 characters or one-hot encoding. So it works okay. But we found that word encoding doesn't help very much because things like cat and car, they're very similar as far as the letters go, but their meanings are not similar. So one change in one character can drastically change the meaning of a word. And so character representations are not all that helpful. So we do word or subword things. And then it's hard because we can't do one-hot encoding. We can't, there are maybe 50,000 words we want to encode. So we train neural networks to encode these. And we try to find encodings where things like walking and walked are in the similar space, in the same way that swimming and swam are in the same space there. And that there are some meaning representation similar to these. So now every time you use like a large language model, it will tokenize all of your words. And that's why nowadays you pay per token. Well, you may not, you probably use a free model, but if you use a paid model, like I'm working on a project where I have an API and we pay per million tokens, not per million words, but per million tokens. And in general, it's about a word a token. It might be, every word is about a token and a quarter, maybe. But that's what's doing where every word is being assigned some vector of numbers to represent it. And that vector numbers is chosen so that it tries to preserve some common relationships between words. Okay, let's get into the activity for today then. So again, there's explore activities for you to explore different things, try out different things. Discussion threads. Besides this week, we're gonna do just job search. It's this time of year is a big time for finding internships and jobs, and so I thought we should do that. Look a little bit at that. So I want you to just find a job posting. It can be in machine learning or data analytics, or anything kind of related to this class. Would be interesting to find. So that's your main option. You can also find anything related to AI news. That would be fine too. I get a lot of AI news in my daily feeds. I don't know if you do too, but yeah, I get a constant stream of updated news articles and stuff like that. So if there's some new AI news thing, feel free to put that in here too. Okay, we're gonna go on the learning notebook and run this practice notebook. And again, just like before, open up the write-up. I'm going to walk you through part of it, or this a little bit, because I find students find this confusing. So again, we're going to open it. We're going to run the libraries at the beginning. And the first part of this comes from a old course and workshop by Jeffrey Heaton on these recurrent neural networks here. So again, we're seeing networks where we have input coming into a network or a node, and then maybe that's sending it to the next layer, and that layer is feeding it back to the previous layer. So we have some feedback, some recurrent connections in these nodes. Another way of thinking of that is we have our inputs and maybe what's called a bias that we're feeding in. We have some hidden layers and output layer. And then every update, we copy the hidden layer into a copy of it. And then we give it a new input and it looks at the copy and from the previous, it'll look at the hidden layers from the previous input and then feed both those to the next update here. So part of this is just having you describe what a recurrent neural network is and how is this different from a traditional neural network. So again, we don't have this feed forward method. We have some sort of recurrent connection here. And what are some of the advantages of these? So again, keeping some history gets you out of what I always think of as like the Dora version where you forget everything oh, you see a new person, that's a brand new person. And so, that's not what we want to do is have some memory of what's going on there. And we need that in order to like generate language or to predict stock prices or anything like that. So, then we're going to get into this example. It's a simple time series. And I think one way I visualize this is basically, let's say you are in and we're looking out the window and we can just see things out the window. Maybe it's a street outside our window and we can just see if there's nothing driving by, it's a 0. And there's maybe 5 different cars that drive by our street. And so if we see a car driving by, we'll see it. So like this is showing a sequence where we start with nothing driving by our window, and then car 3 is there, and then car 3 is still there, and then nothing, and then car 1, and then car 1. So you can think of cars. If you're a car person, you can think of, I often think of like, just watch out my window and there are like 5 different neighbors who walk their dogs by my neighborhood on my street. And so I always look out and oh, there goes, and I don't know who they are. So I just know, well, I know the dogs. There goes the little brown dog, and there goes the white dog, the big white dog and stuff. So again, I'm looking, I don't see, like here I see white dog, nothing, and I'm at a dead end street. So then you turn around and they come back, white dog, and then nothing again. So that sort of input. So again, each one of these lines is a separate observation here. And we are looking outside our window and we're seeing a sequence of predictions. So 2, 2, 1, 1, 0. So you can also think of this as musical notes. We're playing note, note 2, note 2, note 1, note 1, note 0, note 0 out here. And again, note 0 would be maybe not playing anything at all for this. Now, for each of these sequences, we're going to just remember what is the last thing we saw. So again, if we see cars driving by, what was after we see the whole sequence, you ask, what is the last car you saw? Or people walking by or notes played, what was the last musical note that you heard here? So if you heard 1, 1, 3, 3, 0, 0, again, 0 doesn't count. So the last one that was played was a 3 here. So besides this input, our output is also the last one played here. So and sometimes it's really easy, it's the last thing played. 0, 3, 3, 0, 1, 1. The last one thing was a 1. But here, sometimes there's a couple zeros in the way. 0, 0, 0, 2, 2, 0. The last thing you heard was a 2. So that's why we're trying to predict a 2. So again, we're trying to train our network to predict this sort of stuff. So we read in this data, we create our model. And we see how good we are at predicting things. And this is a version without any memory. So you are We have no short-term memory. You are not good at predicting or remembering what the last thing is. You're just guessing here. So this is our guess, and this is what was the correct thing. So we guess, and every once in a while we guess right. We got right this time. We guessed 0 and it was 0. We guessed 0 and it was 1. Oops. It was 0 and it was 2. But here we guessed right again. So we got right a couple times here. But again, we have no memory. So again, we're seeing this data, we have no memory. So then we're going to do recurrent network here. Oh, I guess we can, yeah. So we're going to do the same thing with a recurrent neural network. So now we're going to do a simple recurrent network in here and train it on the data. So here we go. We went through our training. We're going to see how our accuracy looks, and then we're going to see how our predictions work. And with some history there, we're very good at predicting. Not perfect. You know, we got the first one was 0, we predicted 0, 1, we predicted 1, 2, we predicted 2. Here we got, but here it was, we predicted 2, it was actually a 1 there. So what is that? 1, 2, 3, 4, 5, 6, 7. The 7th one. Let's look at the data at that. 0, 1, 2, 3, 4, 5, 6, 7. I think that's this one, where again we have a pretty long history. 2, 2, 1, 1, 0, 0. So we kind of forgot after seeing nothing for a while. We forgot, and maybe we predicted 2 instead of 1 here for that. But this is supposed to show that we can do basic prediction with these GRUs here. Now let's see, what do you have to do? So you describe this. How do you interpret this sequence here? Why, and then the next one, if you have this sequence, why should the output category be 2 for this? Oh, and another thing I didn't mention is as for the outputs, we're doing one-hot encoding for those. So that's what this does. So we're predicting which of, there are 4 different outputs, 0, 1, 2, 3 there. And so we're using one-hot encoding for those. So the actual output for 2 will be 0, 0, 1, 0. So we have a one-hot encoding showing that there isn't a 0, there isn't a 1, there is a 2, but there isn't a 3. So that's what we'll predict. The next one says, try to extend the training period on this. So when we train this one, so this is the training with the simple recurrent neural network. We trained it for 50 epochs, and it did okay. It still got it got a few of them wrong. If I look here, it got correct, wrong. So that's 1, 2, 3, 4. I got 4 wrong here. So each of these, the prediction and the expected class above and below should match. So if we change this, try to change this so it trains it longer, like what did I say? 200 epochs. And then try to run this and see what it gets with that. So, okay, I'll let you play with that, and then we'll move on to section 3, forecasting time series. See if we can predict the stock market with that. So I'll pause for a bit, let you get caught up. Okay, let's see. Yeah, it's gone to the next section, section 3 here. So in section 3, we're going to try to predict actual time sequence or series stuff. So we're going to actually generate these first couple cells here just generate some sample time series. So again, here's our sample time series that we're trying to predict. So again, given this, now each of these are kind of different time series, but again, they're made up by combining a couple common sign functions or signals here. So we combine these signals together to get this. And a good system should be able to recognize, I mean, so you kind of see there's an overall pattern here, and there's an underlying pattern to that here also for this. And so there's these two different patterns that are playing each other. So, and it's causing it. So we don't see a nice up and down and up and down. We see up and down and up and down, but then there's these little, you know, glitches in here also for this. So those are the kind of time series we're going to try to predict here. And again, similar to like predicting a stock price or something like that. Now, the first thing we're going to look at is the naive forecasting prediction. So here's a question for you. If I told you the current weather outside was 33 degrees, what naively would you predict would be the weather temperature next hour if it's 33 degrees right now? Well, the simplest thing, well, you know, you shouldn't guess 70, you shouldn't guess -20. The most, you know, the simplest naive thing to say, well, maybe it's 33 degrees again. If it's 33 degrees now, it might be 33 degrees in the next hour. And again, that actually is not too bad. If you know, you won't get too far off. You predict 33. Temperature is supposed to get up to 40 today there and then back down. But again, it's dropping down to -17, I mean, to 17. So then if you keep guessing 33 every time, after a while, that gets off here. And again, that's what we're doing here is predicting this. You can see these lines, and you can see it ends here, and then the next prediction is the red dot. And again, it is predicting, oh, we were at 0.5, we're going to predict 0.5, and then the little x is where the x value actually was. So again, we're just going to predict it stays the same, and it's not going to be that great. Now, how do we measure how accurate we are for all these predictions? We're going to measure the difference between our prediction and the actual value here. And we're going to just subtract one from the other, find the difference there. Now, the difference might be positive or negative, so we're just going to square it there. So we're going to square the difference of each of these. And again, we use that a lot in distance measurements here. And then we're going to find the average of this distance, this distance, this distance, this distance. And that goes by the name of mean square error. So again, we calculate the error, we square it, and then we calculate the average or mean of all these. So the mean square error here. And with our naive forecasting, we get a mean square error of 0.02, which isn't bad here, but it maybe could be better. So we want the error to be low, and this is pretty low. Can we get it lower than this? So the next thing is to just try to predict with a simple network that's trained, that doesn't have any history, but just looks at patterns in general and tries to flatten all the inputs. So if you look at the whole thing, can you predict it? And you think if it looked at the whole sequence, it should be able to predict what the next, because I mean, in my eye, I can just look at this and I could see this and, you know, just eyeballing it, I think, yeah, it should go down here. So can it kind of learn that sort of idea here? And again, it is doing pretty well. It is predicting down, it's predicting up here. So it is getting a mean square error of 0.004 here. Now, your write-up, which of the above networks had the lowest mean square error? You might want to start noting what these are. And when you run them, you'll get slightly different values here. So if I run this, I might want to start writing, keeping track. So what did naive have? So the naive one here had, okay, we generated a time series. We're forecasting it with naive, and the mean square error was that. And then we tried to just flatten the input. And when you flatten the input, what did we get? I got a mean square error of that. And sometimes when you look at these numbers, it's hard to keep track of which one's lower. So let's try to see if we could. So I was at 0.02 and now I'm 0.004. So 0.004 is less. So that's good. Flattening the input helped rather than just predicting the same thing. Now your job is to look at if you do a simple recursive neural network here, and you train that, what is that mean square error? How does that look as far as the prediction goes? And then a deep recurrent neural network where you have multiple layers of recurrency, can it see kind of this underlying pattern of up and down, and there's a secondary pattern besides the main pattern? Can it detect the secondary pattern very accurately for that with that? And so you want to run that one here. So you want to try out these, and in each one, track down the mean square error. It should be displayed somewhere, and find out which one is the best. The last thing we want to look at it in part 2 is this keep predicting stuff. How good are we at that? This weekend, I'm going to be judging a robotics tournament. And one thing I always find is interesting with robotics tournament is this, what we call compounding error there. We tell a robot to go forward, and it goes forward, but it always turns. It's not ever perfect, so often turns a little bit. And so we're often then the software is predicting, okay, I told it to go forward at this speed, it should be here. I tell it to go forward again, it should be here. I tell it to go forward here, it should be here, there. But there's these compounding errors where every time the robot might turn a little bit. I don't know if you've ever tried walking straight in a field or the woods there, particularly if you can't see the sun or stuff. Like there's some good videos on YouTube of where they block the horizon from people, and they're only allowed to look at the ground. And you look at the ground and you try to see if you can walk straight ahead by just looking at the ground. And you think you're doing really well. You are going. I see the same thing with swimming. I don't know if you've ever been swimming and you're trying to, you go, oh, I'm going to swim right there. You put your head in the water, you swim, and you end up slowly turning yourself all the way around. So you're going like the opposite direction that you think you should there. And that's what we get into when we try to forecast again and again here, where we might be forecasting these values here. So here's our blue line, we're forecasting it and we keep forecasting it. The further we forecast, the more off we get, where the actual results are quite different from that. So again, it is very hard to predict. And again, we see the same thing with weather conditions here. Again, we are trying to predict the temperature in 4 days. And so we are pretty good at predicting the temperature for the next 3-4 hours. But again, if our model is just a little off, there's a little bit something wrong with our model, we don't have some variable in here, our prediction gets off more and more as we go, predicting every hour ahead. And then by 3 or 4 days from now, we're saying it's going to be 50 degrees and it's going to be 10 degrees or something like that. So we get into this problem where we're trying to predict too far ahead of this. And then we see the same thing with our models here that you can try when we're forecasting multiple places ahead. The next section introduces these GRUs and long short-term memory. And again, we used to deal a lot more with these, but again, these are getting a little bit out of favor today. Although just a while ago, I watched some new thing about an updated LSTM network and why it should be, they've modified it so it could be trained very rapidly, which was the problem before. So now we're looking at our models, and again, rather than a traditional recurrent network or a flat network here, we have an LSTM network here, and we're training them. And again, we will start seeing the training being a little slower. And again, we can't necessarily parallelize this. So adding more processors or a GPU or whatever doesn't necessarily help us with this training. It is just going to be slow here. And then we'll try to do our prediction from this. So, and we can try the same thing. Again, we have this long short-term memory and these GRUs, gated recurrent units. Again, they're slightly different in the internal model. They're taking the internal input and then some history, 1 or 2 values from its previous state, and it's predicting some output value. And also sending it some internal state information to its next thing. So the idea is that they have some memory, they're remembering what state they are, and if they see some new input, they can change their current state to a new state here. So we often see like here at time, T-1, so like this would be like last hour, we're trying to predict the temperature. And then this is the next hour, time T, we're trying to predict. So we get some input into the system and we get the internal state from the last hour and we're trying to predict the temperature. And then here's the hour after that. We're given some new information and some the state of the system from the previous update or time prediction. We're going to predict the next hour's value. So again, run through this. Again, training will be slow and you can do the predictions. And again, we want you to describe a little bit of the difference. Again, and you can read this. AI also does a pretty good description of the difference between LSTM and a traditional recurrent neural network. Same here. And what problems are we trying to solve? One thing we see a lot with this stuff is our networks forget over time. And they just pay attention maybe to the most recent stuff and they don't remember past stuff. And if there's nothing interesting happen, they'll kind of forget everything that's happened there. Where LSTMs and GRUs are supposed to maintain some state, some memory of what is, and they will not change that until some new kind of interesting value pops up, and some new value will pop up and will kind of reset its internal state, and we'll see something else. So, oh, okay, this is still training. The last part is optional here, and that's sunspot prediction here. So so again, sunspot are these activities they on the sun, and they often show up as dark spots on the sun, right? And they follow a predicted pattern of the number of sunspots. And it's a cyclical, like 11-year pattern here. And our pattern is actually just really increasing now for that. And so we're going to grab the raw sunspot data here, bring it all in, process it. Here's the sunspot data, monthly sunspot activity for the last, I don't know, 30 years, I think. I don't know, more than that, 100 years. And then we're going to try to predict the sunspot activity going ahead. So the orange is the actual stuff, and the green is our prediction going forward for this. So we're going to try to change the network and predict that. And so we're going to try to generate some graphs of that here, showing our predicted values and the actual values, seeing if we can capture that sort of stuff. Our current network here doesn't actually do very well. It's a very simple network, but you can try out different versions. Well, actually, the version here has some long short-term memory network that should be better than just the simple recurrent neural network processing here. Now you're wondering, why do I care about the sunspot stuff? Why do you care about the sunspot data? And do you know why you might care about the sunspot data? Well, if they were really bad, they could be dangerous, I guess. But that is not why I have an app on my phone. Yes. So last night I get an aurora forecast. If the aurora is looking good. So again, people are monitoring this, and then they're predicting the northern lights. And again, if we get these corona mass ejections or what, if we get some activity there that sends new particles towards us and they align towards us, those, the magnetic field on Earth are going to pull those around to the poles, and we'll get some nice northern lights. So what was it, last April we had the really good, I don't know if anyone got out to see the northern lights last April. Really? Yeah. List. Don't see the date. Yeah, it was either April or May, but yeah, this is what we were seeing last year around in April, May, when we were doing the northern lights. So okay, so today we want you to go through this and finish up the write-up. Again, it's going to take some time, especially when you get to part 4 for this stuff. And again, this is the same technique that is then used to predict the next character and then eventually word in a sentence. With this, if we can predict this next value here, we can predict, the next word in a sentence for that. And once we start doing that, we're getting into this is the framework that's going to lead to what we call transformers, which are what all large language models run here. So the next week, we're going to probably start looking at transformers. I'm trying to remember what. Yeah, because we actually covered. So next week, I'm going to move Unit 9 up to Unit 8, and we'll do transformers next unit for that. So we can start doing it. Okay, I'm going to stop sharing for a while and let you work on this write-up, let you train your network, see if you do, and that's all we'll be doing today.